Usually when we think about computer chips, there's this underlying expectation of physical certainty. Like, it's helpful to picture microscopic plumbing for a second.
Right, yeah, like predictable pathways.
Exactly. You have the pipes, which are the wires, and you have the valves, which are the transistors, and the electricity flows, or it doesn't.
Right.
It's water on or water off, 1 or 0. But the moment you step into the world of subatomic physics, that entire microscopic plumbing system is just completely broken.
It's entirely out the window.
Yeah. We end up looking at this computational landscape where the water is somehow like both flowing and not flowing at the exact same time. And, well, quite possibly teleporting through the sides of the pipes.
Which is a terrifying concept for an engineer, because it forces us to just throw out the entire classical rule book. I mean, we are no longer just making that plumbing smaller. We're fundamentally redefining what plumbing even means at the quantum scale.
Right.
Humanity is currently crossing this threshold of what physicists call the second quantum revolution.
So welcome to Audio Notebook. Our mission for you today is a massive one. We are stepping into the absolute cutting edge of computational physics to, separate the extreme sci-fi hype from the urgent physical realities of quantum computing.
And there is a lot of hype.
Oh, an unbelievable amount. We want to give you a clear map of what is actually happening in these laboratories right now. And that framing you just used, the second quantum revolution, that implies we've already survived the first one, right?
We have, yeah. And it's really important context, because that first revolution, it gave us the foundational physics to engineer macroscopic technologies that, frankly, you use every single day.
Like what?
Well, semiconductors, for one. The lasers firing down fiber optic networks.
Yeah.
The MRI machines in your local hospital. Even the atomic clocks that keep your GPS accurate.
Oh, wow. I didn't realize GPS relied on that.
Yeah, all of those rely on a broad statistical understanding of quantum mechanics. Like, we used quantum rules to build big physical things that act in predictable, aggregated ways.
So millions of atoms working together.
Exactly. Bulk behavior.
Okay, so the distinction with the second revolution then is isolation. Because instead of relying on the bulk behavior of a billion atoms, researchers are talking about the direct microscopic manipulation of individual isolated quantum states.
Right down to the single particle.
They are literally harnessing phenomena like superposition and entanglement to actively process information. And, a lot of this aggressive innovation feels born out of a looming physical wall. Like, we hear all the time that Moore's law is dying.
It is dying, and strictly due to the laws of physics. Because for, over half a century, the semiconductor industry relied on this relentless march of miniaturization.
Just making things smaller and smaller.
Right. You shrink the silicon transistor, you pack more of them onto a chip, and your computing power doubles. But as engineers shrink those transistors down to a scale measured in nanometers, where the transistor gates are just like a few atoms thick, the physical world stops acting deterministically.
So let's unpack what that physical wall actually looks like for you. Imagine the gate of a transistor as a physical door, right? And it's holding back a crowd of people, which represents our electrons.
Okay, I like this analogy.
In classical physics, if the door is closed, the people stay in the hallway. That's a perfect 0. But when that door gets shaved down to a thickness of just a few atoms, you run into something called quantum tunneling.
The dreaded quantum tunneling.
Right. The electron doesn't need to open the door anymore. It phases right through it. It ignores the physical barrier entirely.
Which completely destroys your classical binary logic.
Yeah.
I mean, you cannot maintain a reliable 0 or 1 if your electrons are spontaneously teleporting to the other side of the gate.
It's chaos.
It is.
Yeah.
For decades, the semiconductor industry viewed quantum tunneling as this catastrophic nuisance, a manufacturing error that had to be aggressively engineered around. The paradigm shift of quantum computing is looking at those bizarre subatomic behaviors and deciding to just stop fighting them.
If you can't beat them, join them.
Exactly. Instead of forcing an electron to act like a classical valve, they're letting the electron act like an electron.
By engineering systems that natively operate according to the probabilistic laws of quantum mechanics, we unlock a capacity to solve specific classes of problems that would take a classical supercomputer literally billions of years to crunch.
Billions, yeah.
But if we aren't using silicon valves, I'm trying to picture what actually sits on the motherboard. Like, what does the hardware of a quantum bit, a qubit, physically look like?
Well, to visualize the hardware, you first need to look at the fundamental unit of classical data.
Okay.
So a classical bit is instantiated through a complementary metal oxide semiconductor, a CMOS transistor.
The standard chip.
Right. It dictates a deterministic flow of voltage. Low voltage is the ground state, representing 0. High voltage is the excited state, representing 1.
On or off.
Right. Every digital action you take, from streaming a video to running an advanced AI model, translates back to billions of these rigid light switches.
But a QUIP is completely alienated from that structure. I mean, researchers aren't stamping out standard chips anymore. They are isolating wild, microscopic phenomena.
Very wild.
Let me list a few of these modalities for you because the sheer variety is just staggering. Some laboratories, they capture a single electron inside a microscopic cage called a silicon quantum dot.
Which is incredibly hard to do.
And they use the direction that electron is spinning to hold the data. Other teams use the polarization state of a single photon of light.
Right, photonic qubits.
Then you have these setups where neutral atoms are held perfectly suspended in a vacuum by crossing laser beams, a technique they actually call optical tweezers.
It sounds like sci-fi, but it's happening right now. And those are all viable, but we should also probably spotlight the modality currently leading much of the commercial scaling race, which is superconducting qubits.
Ah, right, the ones IBM and Google use.
Exactly. This architecture involves pushing oscillating microwave currents through a tiny superconducting loop. And inside that loop is a microscopic gap known as a Josephson junction.
A Josephson junction.
Yeah. Pairs of electrons, called Cooper pairs, they tunnel across that gap, and that creates a highly controllable quantum state.
So whether you are dealing with a levitating atom or a supercooled circuit loop, the defining characteristic remains the same. The qubit is not restricted to a binary either-or state. It exists in a linear combination, a superposition of its basis states.
And we really need to introduce the underlying math here, but we will keep it entirely grounded in what it physically means.
Please do.
The state of a single qubit is defined by an equation. Psi equals alpha times the kit of 0, plus beta times the kit of 1.
Okay, let's translate that equation so you can visualize what the hardware is actually doing.
Yeah.
Psi just represents the overall state of the qubit, right?
Yeah.
And the kit of 0 and kit of 1, those are just standard physics notation for the baseline 0 and 1 states. But alpha and beta are the driving forces here. They are probability amplitudes, and the math dictates that the squares of their absolute magnitudes equal the probability of that qubit collapsing into a solid 0 or a solid 1 when you finally measure it.
Yeah, and that term probability amplitude, it requires a critical distinction. Because in classical statistics, a probability is just a flat percentage, like a 50% chance of rain.
Sure.
But alpha and beta are complex numbers. This means they possess not just a magnitude or a size, but also a geometric phase.
A phase, like they point in a direction.
Exactly. They point in a specific direction.
Yeah.
And this phase is the engine that allows the qubit to exhibit wave-like interference behavior.
And the scaling of this complex state space is where human intuition just simply breaks down. Like if you have a classical register of 3 bits, it can hold one specific permutation at a time, say 0, 1, 0.
Right.
It can rapidly switch, but at any given millisecond, it only holds one of 8 possible combinations. But a quantum register of 3 qubits holds a superposition of all 8 permutations simultaneously.
It holds the whole space.
Yeah. And if you scale that up to just a few hundred qubits, the number of simultaneous states exceeds the number of atoms in the observable universe.
It's mind-boggling. And because that state space expands exponentially with every single qubit added, it naturally generates the most pervasive and arguably the most damaging public misunderstanding about the field.
Oh, the sci-fi myth.
Yes, the myth.
Every movie and pop science article tells you that a quantum computer is incredibly fast because it splits into parallel universes, tries every single possible answer at the exact same time, and then magically presents the right one.
And we must unequivocally dismantle that concept today. It is scientifically false.
Not true at all.
No. If a quantum computer simply calculated every possible answer equally within a massive superposition, and then you measured the system, the wave function would collapse probabilistically. You would receive a completely random output. It would be total garbage data.
You'd essentially be rolling a die with a billion sides and just hoping you hit the jackpot.
Exactly.
That isn't computation, that's a lottery. So if the machine isn't trying everything at once, what is the actual mechanism driving this immense computational power?
The true mechanism is wave interference. A quantum processor is fundamentally an interference engine. Because these probability amplitudes possess phase, they behave analogously to ripples in a pond.
Okay, ripples.
The computational art lies in algorithmically manipulating these amplitudes so they dynamically interact with one another before you ever take a measurement.
I want to give you a tangible analogy to hold on to here because this is the core of it all. Imagine you are tasked with navigating a complex maze. Classical computing is akin to walking down every single path one by one.
Right.
You hit a dead end, you backtrack, you try the next corridor. It is agonizingly slow. Now, the sci-fi parallel universe myth suggests quantum computing clones you a million times so you can run down every corridor simultaneously.
Which we just established is false.
Right. But the physical reality is profoundly different.
The physical reality operates on the principles of acoustic resonance.
Yes. Picture the quantum algorithm flooding the entire maze with a massive wave of fluid. The architecture of the algorithm acts as the walls of the maze. As the waves travel down the wrong paths, the dead ends, they bounce back.
They reflect.
And the algorithm is precisely engineered so that when those wrong answer waves reflect, they are perfectly out of phase with each other. The crest of one wave crashes into the trough of another wave.
Destructive interference.
Exactly. This creates destructive interference. The waves cancel each other out, and the wrong answers literally erase their own probabilities from existence.
Concurrently, the corridors leading to the correct answer are engineered to align in phase. Crest meets crest, trough meets trough.
Destructive interference.
Yes. The waves compound and amplify, much like an acoustic resonance chamber where a specific frequency builds to a deafening volume.
So by the time the algorithm finishes its silent choreography and you finally look at the system to take a measurement, the correct answer is the only mathematical reality left standing.
It's the only wave left.
The probability of the right answer has been amplified to near 100%, while the probability of all the incorrect answers has been flattened to zero. It doesn't blindly test options, it dynamically sculpts the probability landscape.
It is an incredibly elegant mathematical choreography. However, executing that choreography introduces arguably the most severe physical obstacle in the entire discipline.
Which is?
You are attempting to balance these delicate probability waves across isolated subatomic particles, and the ambient physical universe is chaotic and aggressive.
Right. Which brings us to the extreme thermodynamics of decoherence, specifically the mandate to chill these systems to 15 millikelvin.
It's absurdly cold.
Let's ground that number for you. Absolute 00 Kelvin is the theoretical floor of physics where all atomic movement permanently halts. If you travel into the deepest voids of outer space, far from any star, the ambient temperature is roughly 2.7 Kelvin, gently warmed by the cosmic microwave background radiation left over from the Big Bang.
Which is pretty cold.
But 15 millikelvin is a microscopic fraction of a single degree above absolute zero. It is drastically colder than deep space.
And that extreme cryogenic environment isn't like a cautious engineering preference just to keep the processor running smoothly. It is a strict thermodynamic imperative, especially for the superconducting transmon qubits we detailed earlier.
Why is it so strict?
Well, digital information in those circuits is encoded in unimaginably minuscule energy gaps between quantum states, and the processors operate at microwave frequencies, typically around 5 gigahertz.
So the physical energy difference distinguishing a 0 from a 1 is vanishingly small.
It is incredibly fragile. Imagine bringing that processor into a standard room temperature laboratory.
Okay.
The ambient thermal energy in that room is orders of magnitude larger than the qubit's delicate transition energy. It would be like trying to balance a house of cards in the middle of a Category 5 hurricane. Ambient thermal photons, particles of heat and light from the environment, would just bombard the qubit. This chaotic energy transfer causes the qubit to spontaneously jump from a 0 to a 1, creating a bit flip.
Just randomly changing the data.
Yes, or even more subtly, it causes the qubit to lose its phase alignment, resulting in a phase flip.
And a phase flip is fatal, because if the phase shifts randomly, our beautiful maze analogy collapses. The waves stop aligning, the crests miss the troughs, and the constructive interference dissolves.
The calculation dies.
This bleeding of the isolated quantum state out into the messy, noisy classical environment is what physicists call decoherence.
Decoherence is the sudden death of a quantum calculation. Beyond protecting the phase, the actual hardware circuits rely on superconductivity, the complete absence of electrical resistance.
Right.
And that physical property only manifests in specific metals when they're brought right to the brink of absolute zero.
This creates a really fascinating visual contrast if you ever look at photos from these labs, because the actual quantum processor chip is remarkably small, no bigger than a standard silicon CPU. but the infrastructure required to run it is colossal.
Fridges are huge.
They use these massive machines called dilution refrigerators. They look like giant steampunk chandeliers composed of stacked gold and copper plates.
And those chandelier structures employ a continuous closed-loop mixing cycle using helium-3 and helium-4 isotopes. The isotopes undergo a thermodynamic cycle that constantly extracts heat from the processor, which is mounted at the very bottom, the deepest, most isolated plate of the array.
And they need all that volume just for shielding, right?
Exactly. The sheer volume of the refrigerator is dictated by the need to shield that tiny silicon chip from ambient thermal noise, electromagnetic radiation, and even the subtle interference of the Earth's natural magnetic field.
But even locked inside that extreme isolation, the qubits still suffer from state degradation. The window of time you have to execute your algorithm before the environment inevitably corrupts the data is called the coherence time.
And for legacy industrial processors, that coherence time has historically been brutally restrictively short.
Measured in microseconds.
Right. Solving that short coherence time requires looking beyond the refrigeration and examining the physical materials making up the processor itself. The substrate, the foundation the qubit is printed on, plays a massive role.
Okay, what were they using?
Well, for years, engineers fabricated superconducting transmon qubits using aluminum traces deposited onto a sapphire substrate. It functioned, but it harbored a hidden, fatal flaw.
The dielectric defects.
Precisely the issue. The interface between the aluminum and the sapphire naturally generates microscopic atomic scale imperfections, frequently categorized as two-level systems.
Two-level systems, what do they do?
Functionally, these defects act as parasitic sponges. As the delicate microwave energy oscillates through the circuit to perform a calculation, these microscopic sponges trap and absorb the energy. They literally drain the life out of the qubit, dramatically accelerating the decoherence timeline.
But in early 2025, researchers at Princeton University executed a massive pivot in material science to solve this. They threw out the traditional aluminum and replaced it with a metal called tantalum.
Tantalum.
Furthermore, they abandoned the sapphire and deposited the tantalum onto a high-purity silicon substrate.
And the underlying chemistry of why tantalum succeeds where aluminum fails is fascinating. During the fabrication of these microscopic circuits, the chips must undergo harsh acidic cleaning procedures to strip away surface contamination.
To make them perfectly clean.
Right. But aluminum degrades slightly under those acid washes, which exacerbates the formation of those microscopic sponges. Tantalum, however, exhibits exceptional chemical robustness. It survives the acid wash flawlessly, maintaining its underlying superconducting properties without forming the parasitic defects.
And the resulting metric is staggering. By neutralizing that dielectric loss, the tantalum on silicon architecture successfully breached the 1 millisecond coherence barrier.
A huge milestone.
That effectively means the qubit maintains its quantum state nearly 15 times longer than previous legacy processors. They bought the interference engine 15 times more time to choreograph its waves before the environment collapses the calculation.
Extending that calculation window fundamentally alters what these machines are capable of achieving. Because as we keep the qubits alive longer and network larger arrays of them together, we approach a critical threshold.
Which naturally brings us to the subject that terrifies the global intelligence community. When we finally string enough of these stable qubits together, we confront cryptographic collapse.
The nightmare scenario.
Right. To understand why this is viewed as an existential threat to digital privacy, we have to look at the locks currently securing the internet. I'm talking about RSA and elliptic curve cryptography, or ECC.
These protocols are the absolute bedrock of global digital security. They secure not just your personal banking passwords, but the vast majority of the internet's routing infrastructure, international financial wire transfers, and the highest tiers of classified diplomatic communications.
And the security of those protocols rests entirely on one simple mathematical asymmetry involving prime factorization. Like, it is computationally trivial to take two massive prime numbers and multiply them together. A basic smartphone can execute that in milliseconds.
Sure.
The result is a gigantic composite number, which functions as your public key, but the security relies on the reverse operation. If I hand you a massive 2048-bit integer and ask you to calculate the two specific prime numbers that created it, a classical computer is essentially helpless.
Completely helpless. Classical algorithms rely heavily on trial division, methodically checking numbers one by one to see if they divide cleanly. For a 2048-bit integer, The search space is so astronomically large that it is estimated the fastest classical supercomputer on Earth would require billions of years of continuous processing to find the correct factors.
So the math provides an impenetrable shield.
That shield held perfectly until 1994, when a mathematician named Peter Shor published an algorithm that changed the entire trajectory of computational physics.
Shor's algorithm?
Yes. He proved mathematically that a sufficiently powerful quantum computer could factor those large integers not in billions of years, but in polynomial time. We are talking about reducing billions of years down to hours or days.
How does it even do that?
Well, Shor's algorithm achieves this devastating speed up through a brilliant pivot. It does not attempt to attack the factoring problem directly. Instead, it utilizes number theory to translate prime factorization into a period-finding problem over a modular function.
Okay, wait.
The core function is f of x equals a to the power of x modulo n.
Let's break down that modular function for you using a clock, because modular arithmetic is basically clock math.
Exactly.
A standard clock operates modulo 12. If it is 10 o'clock and you add 4 hours, you don't say it's 14 o'clock. The numbers wrap around, returning to 2 o'clock. That repeating wrapping behavior creates a cycle, or a period. Peter Shor realized that the secret prime factors of an RSA key are mathematically hiding inside the repeating period of that specific modular function. If you can discover the frequency of that cycle, you can extract the primes.
But there's a catch.
The problem is, finding that period using classical computers is just as computationally impossible as factoring the number itself.
Exactly. But for a quantum processor, finding a repeating period is a perfect target for an interference engine. Shor's algorithm deploys a highly sophisticated subroutine known as quantum phase estimation.
QPE.
Yes, which heavily incorporates the quantum Fourier transform, or QFT.
Oh, this is where our maze and acoustic resonance analogy comes roaring back.
Yes, the quantum processor initializes a massive superposition containing all possible inputs to that modular function. Through a precise algorithmic sequence of unitary logic gates, it applies the quantum Fourier transform.
And what does the QFT do?
The QFT is mathematically designed to induce destructive interference among all the incorrect, non-periodic outcomes. The probability waves of those incorrect answers clash, cancel out, and drop to zero.
While the correct ones amplify.
Right. Simultaneously, it drives constructive interference to amplify the probability of the correct period, which mathematicians refer to as R.
The waves representing the correct period stack on top of each other, building a massive probability spike.
So when the processor finally measures the system, the wave function collapses directly onto that correct period. The quantum computer's heavy lifting is now complete.
And then?
A standard classical processor takes that period, applies straightforward number theory specifically, calculating continued fractions, and trivially deduces the original prime factors. The encryption is entirely broken.
It is an elegant, devastating mathematical weapon. But executing Shor's algorithm on a mathematically complex 2048-bit RSA key requires an incredibly powerful, deeply stable quantum computer.
Which we didn't have.
Right. For years, the timeline for building such a machine was a source of great comfort. Let's trace how that timeline, the comfort margin, has violently collapsed.
The comfort margin represents the buffer time intelligence agencies believe they had to migrate global infrastructure before the threat materialized. In 2019, researchers at Google published a comprehensive resource estimation. Accounting for the massive amount of noise and required error correction, they estimated that executing Shor's algorithm on RSA TUM48 would require roughly 20 million physical superconducting qubits operating continuously for 8 hours.
20 million qubits. I mean, in 2019, the most advanced quantum processors barely possessed 50 physical qubits. So the industry breathed a collective sigh of relief. A 20 million qubit machine implies a dilution refrigerator the size of an Amazon fulfillment center.
It felt decades away.
But then, researchers began optimizing the algorithmic compilation. The surface codes used for error correction became vastly more efficient. By early 2025, that estimate of 20 million physically required qubits plummeted to just 1 million.
That alone is a staggering contraction in a 6-year window. But the threat landscape was fundamentally redefined by a shockwave in late 2025 and early 2026, stemming from advancements in neutral atom architectures.
Oh, this is the specific development that keeps cybersecurity experts awake at night?
Yeah. Theoretical researchers combined Shor's algorithm with highly efficient quantum low-density parity check codes, QLDPC.
Okay.
When they modeled running this combination on a neutral atom architecture, where the qubits are atoms held by mobile optical tweezers, they realized that dynamic reconfigurable connectivity changes everything.
Because it can move.
Right. Unlike rigid superconducting chips, lasers can literally transport atoms across the vacuum chamber mid-computation, allowing them to interact with distant qubits.
When they ran the math on this highly mobile dynamic architecture, the hardware requirement to execute Shor's on a standard elliptic curve ECC256 key dropped from millions of qubits down to an astonishingly low range of just 10,000 to 26,000 physical qubits, and resolving over a matter of days.
Operating a fault-tolerant array of 10,000 physical qubits is still an immense, unachieved technical hurdle today. We are not there.
No.
But dropping the requirement from 20 million down to 10,000 in half a decade, the intelligence community's comfort margin simply vanished.
I have to pause here and ask the question you're probably yelling at your speakers right now. If we just established that we do not currently possess a fault-tolerant machine with 10,000 perfectly controlled qubits, then practically speaking, my banking data and private messages are safe right now, correct? The lockpicking machine doesn't physically exist yet.
Well, that assumption raises a chilling distinction regarding modern cyber warfare. The lack of a functioning quantum computer today offers absolutely no protection for the data you are transmitting today.
Great, why not?
Because the globe is currently enduring what the NSA and the Cybersecurity and Infrastructure Security Agency recognize as the HNDL threat model.
HNDL, harvest now, decrypt later.
Yes. HNDL is an asymmetric temporal cyber weapon. It fundamentally decouples the act of data theft from the act of decryption. We possess concrete evidence that nation-state adversaries and advanced persistent threat groups are actively intercepting, siphoning, and hoarding vast troves of encrypted classical data as it traverses global fiber optic networks.
You have to view this through the lens of a data shelf life. Imagine a government transmitting a highly classified diplomatic strategy, or a pharmaceutical corporation sending the molecular schematics for a next-generation biologic, or, a hospital transferring a massive anonymized genomic database.
High-value data.
Exactly. For that data to retain its value or security, it requires a shelf life of, let's say, 25 years.
But if a cryptographically relevant quantum computer, a CRQC, comes online in just 10 years,
then your data is actively breached today. It is entirely irrelevant that the adversary cannot read the file right now. They are stealing the locked safe, transporting it to a massive state-sponsored digital warehouse, and patiently waiting 10 years until they forge the key.
Until Q-Day.
Exactly. When Q-Day finally arrives, they will systematically deploy Shor's algorithm against their historical archives. They will retrospectively decrypt decades of the world's most sensitive communications.
And because of this dynamic, international intelligence agencies view HNDL not as a hypothetical future scenario, but as a severe ongoing data breach occurring in real time. The information being harvested today is already fundamentally compromised.
This stark realization has triggered an absolute zero-sum global arms race. The geopolitical stakes are difficult to overstate. Whichever nation crosses that fault-tolerant threshold first will gain an unprecedented intelligence hegemony.
Absolute dominance.
They will possess the capability to read their adversaries' historical and present secrets, while simultaneously using quantum technologies to render their own data mathematically impenetrable.
The United States has aggressively mobilized capital into national infrastructure. Initiatives like the Quantum Systems Accelerator and DARPA's Quantum Benchmarking Program are explicitly targeting utility-scale, fault-tolerant systems to ensure the U.S. maintains cryptographic parity.
But China is demonstrating massive state-backed progress across diverse hardware architectures. The Chinese Academy of Sciences has deployed photonic machines, the Zhuheng 3.0 and 4.0 systems, which manipulate photons of light to achieve massive speedups in highly specialized sampling tasks.
And their advancements in superconducting circuits are equally formidable. The Zhuheng 3.0 processor is a 1/5 qubit system, demonstrating exceptional single qubit and 2 qubit gate fidelities.
Right, the random circuit sampling.
Yeah, in random circuit sampling benchmarks, its performance firmly rivals and in specific metrics surpasses the leading processors developed by Western corporations. It is a genuine, heavily resourced bilateral race.
So if the encrypted data of today is already being harvested and stockpiled, how does the world stop the bleeding for the data of tomorrow? How do we build new locks?
That necessity catalyzed the defensive counter-revolution, specifically a massive global engineering migration toward post-quantum cryptography, or PQC.
Post-quantum cryptography is essentially fighting exotic math with different exotic math. We know quantum computers use interference to efficiently dismantle prime factorization and period finding. So the cryptography community had to invent entirely new cryptographic locks utilizing mathematical structures that quantum computers are fundamentally terrible at solving.
And this transition is no longer theoretical. It is an active, urgent, global deployment. Following an exhaustive 8-year evaluation process spanning the globe, the U.S. National Institute of Standards and Technology, NIST, finalized its first 3 principal PQC algorithms in August of 2024.
The FIPS standards.
Yes, these algorithms are now mandated under Federal Information Processing Standards, or FIPS.
These 3 standards are the new architectural foundation of the internet. Let's walk you through what they actually do. First is FIPS 203, known as ML-Chem, which evolved from the Crystal's Kyber submission.
For key exchange.
Right. This protocol handles key exchange. It replaces vulnerable classical algorithms like Diffie-Hellman, allowing 2 computers communicating over a hostile public network to securely shake hands and establish a confidential session.
Next is FIPS 204, designated as MLDSA, based on the Crystal's dilithium algorithm. This standard provides identity authentication and digital signatures.
How does that work in practice?
Well, when your computer downloads a firmware update and needs to definitively verify that the code originated from Apple or Microsoft rather than a malicious third party, it relies on a digital signature. MLDSA replaces the deeply vulnerable RSA and ECC signature schemes.
Okay, and finally, there's FIPS 205, or SLH-DSA, based on FINS NCS+. This one is fascinating because it acts as the ultimate parachute.
It's the backup plan.
NIST knows that mathematics evolves, and there is always a chance someone finds a flaw in the new math powering the first 2 standards. So FIPS 205 is a stateless, hash-based signature scheme. It relies on a completely alien mathematical foundation compared to the others. It serves as a robust, conservative fallback protocol just in case the primary algorithms are eventually broken.
Right. And the new math-powering ML-Chem and MLDSA is primarily rooted in the geometry of multidimensional lattices. Specifically, they rely on complex computational hurdles known as the learning with errors problem and the shortest vector problem.
I want to try and visualize this lattice math for you because the geometry is incredibly clever. A lattice is basically a repeating grid of points. In 2 dimensions, it's just a sheet of graph paper.
Simple enough.
Finding the shortest line between 2 specific intersections on graph paper is trivial. But these cryptographic lattices don't have 2 dimensions. They possess hundreds, sometimes thousands, of spatial dimensions.
The problem is fundamentally geographic rather than periodic. A quantum processor easily collapses the neat, repeating, periodic structure of integer factorization using the quantum Fourier transform. But finding the shortest coordinate vector hidden within a chaotic high-dimensional lattice lacks that repeating symmetry.
So no resonance.
Exactly. It does not possess the neat periodic structure that Shor's algorithm actively exploits. The probability waves have no clean pattern to resonate with, rendering the interference engine essentially blind to the solution.
So the math is incredibly robust on paper. But here is where theoretical cryptography violently collides with real-world plumbing. Attempting to seamlessly upgrade the entire global internet to use these new lattice locks has unleashed an engineering nightmare known as cryptographic bloat.
Cryptographic bloat is a severe structural overhead issue. To maintain their security margins against potential future quantum attacks, ML-Chem and MLDSA require significantly larger public keys and ciphertext sizes compared to the legacy classical keys they are replacing.
To put the scale of this into perspective, consider a standard TLS handshake. That is the invisible security protocol that fires every single time your browser loads a secure website.
Right, it happens instantly.
Your browser and the server quickly swap RSA or NCC keys. Those legacy keys are tiny. They easily slide into standard internet transmission envelopes, the basic data packets traversing the web. But these new PQC lattice keys are massive. They frequently exceed the standard maximum transmission unit, or MTU, of standard network protocols.
And when a data packet exceeds the strict MTU limit, the network router executes packet fragmentation. A single cryptographic key is violently sliced apart and distributed across multiple TCP segments or UDP datagrams.
And the physical infrastructure of the internet absolutely despises fragmentation. If you are operating on a high-latency mobile connection, or your data must pass through rigid corporate middle boxes and legacy firewalls, fragmentation causes chaos.
It's chaos.
A legacy firewall inspects a fragmented packet containing a massive, unrecognizable cryptographic key, assumes it is a malicious buffer overflow attack, and simply drops the packet. the handshake dies. The website fails to load.
which is unacceptable for global commerce.
This bloat causes widespread latency degradation and unpredictable connection failures across older infrastructure.
Mitigating these infrastructure limits requires deploying a deeply complex hybrid transition phase. Network engineers are currently forced to blend legacy classical encryption simultaneously with PKC inside the exact same handshake.
So doing it twice.
Yeah. This redundancy ensures the session remains secure against quantum harvest now decrypt later attacks, while maintaining backward compatibility for older hardware until the global routing infrastructure is entirely updated and verified as quantum agile.
Which could take over a decade of grinding infrastructure work. Okay, let's take a breath. Cybersecurity is a high-stress, zero-sum arms race, but I want to pivot entirely. Because when Richard Feynman first proposed the concept of a quantum computer back in 1981, his goal wasn't to break banking passwords or stress-test internet routers. What was the actual visionary promise of this technology?
Well, Feynman famously postulated a profoundly simple, yet revolutionary observation. Nature, at its fundamental level, isn't classical. The universe operates on the laws of quantum mechanics. Therefore, if you wish to simulate nature accurately, you cannot use the classical machine. You require a quantum machine.
This observation is the key to the true economic, medical, and scientific promise of quantum hardware. Currently, humanity spends billions of dollars building massive classical supercomputers, specifically to simulate molecular chemistry and biology. And despite that massive investment, classical physics continually hits a hard wall.
They hit a wall because classical supercomputers are forced to utilize approximation methods, such as density functional theory or DFT.
And what does DFT do?
DFT attempts to roughly approximate the electron density of a molecule rather than rigorously tracking the physical state of every single interacting electron. That approximation works adequately for small, simple molecules. But when researchers attempt to model complex molecules, vital proteins, or novel battery chemistries, the electrons are highly correlated and deeply entangled.
Too many variables.
Tracking the exponential explosion of these entangled interactions requires classical memory capacities that quickly exceed the total number of atoms in the observable universe. It is physically impossible to classically simulate complex chemistry with perfect fidelity.
But a quantum computer doesn't need to approximate. It natively speaks the fundamental language of the molecule. It maps what physicists call a molecule's Hamiltonian, the total energy operator, accounting for the kinetic and potential energy of every electron directly onto the qubits.
Yeah.
You aren't building a rough model of the chemistry. You are physically instantiating a digital quantum twin of the molecule inside the processor.
By establishing that native quantum twin, researchers can extract highly accurate ground state energies, map complex orbital behaviors, and model dynamic reaction pathways that classical computers simply cannot resolve. The implications for redesigning the pharmaceutical pipeline, for instance, are staggering.
The modern drug discovery pipeline is notoriously slow, staggeringly expensive, and predominantly ends in clinical failure, largely because our biological modeling is classically inaccurate. But in 2024, a landmark publication in Nature Physics blew the doors off this limitation. Researchers deployed a hybrid quantum classical pipeline to specifically target a notorious cancer mutation.
They targeted the KRAS G12C mutation.
Right. For decades, the KRAS G12C protein was widely deemed an undruggable cancer driver. Its physical structure is wildly complex, and the binding pockets on the protein are simply too shallow for traditional small molecule drugs to attach to effectively.
Utilizing a superconducting quantum processor, the research team bypassed classical approximations and accurately modeled the complex molecular interactions required to design covalent inhibitors. By natively mapping the covalent reactivity and the incredibly subtle electron polarization of the protein's transition states, nuances that classical models entirely blurred over, they identified highly viable, optimized drug candidates.
They successfully predicted molecular behaviors that classical methods failed to see, firmly proving that quantum hardware can navigate vast, previously uncharted chemical spaces to fight untouchable diseases.
It is quite literally saving lives at the subatomic level, and the applications span far beyond medicine.
Right, like batteries.
Yes. The global transition to clean energy is severely bottlenecked by battery technology. We desperately need higher energy densities, dramatically faster charging cycles, and the stability of solid-state architectures. In late 2024 and 2025, researchers aimed quantum algorithms directly at battery chemistry. They successfully simulated the reductive decomposition of ethylene carbonate.
Ethylene carbonate is a critical, yet highly unstable, liquid electrolyte component utilized in standard lithium-ion batteries. By precisely mapping its highly correlated electron states as the battery undergoes its charge cycle, the quantum simulations revealed deeply hidden electrochemical degradation mechanisms.
If you understand the exact quantum mechanics of how the electrolyte breaks down, you open direct engineering pathways to design stable, solid-state batteries that can charge in minutes and resist degradation over decades.
I also love this next application because it represents quantum computers being utilized to design superior classical computers. It's incredibly meta. In 2025, an Australian research team validated an architecture known as a quantum kernel-aligned regressor model, a QKR.
The QKR architecture is a brilliant practical application of quantum machine learning. The team applied this model to assist the physical fabrication of gallium nitride, or GaN, high electron mobility transistors.
The hurdle with classical machine learning in this context is that physical semiconductor fabrication yields incredibly scarce, highly nonlinear experimental data. If you only possess, say, 159 physical experimental samples measuring a semiconductor's ohmic contact resistance, a standard classical AI model will heavily overfit the data.
It memorizes the noise.
Exactly. It essentially memorizes the random noise in the sparse data instead of learning the underlying physical pattern. But the QAR model, natively utilizing the high-dimensional parameter space of quantum mechanics, successfully generalized the pattern from just those 159 samples. It accurately predicted the contact resistance and successfully guided the physical manufacturing of highly optimized classical chips.
It serves as definitive proof that quantum simulation is no longer relegated to theoretical chemistry on a chalkboard. It is actively yielding tangible, optimized results in advanced industrial manufacturing.
While all of these simulations modeling undruggable cancer proteins, mapping battery electrolyte degradation are incredibly exciting, they represent long, complex algorithms. Which brings me back to the massive elephant in the room. How are these machines not succumbing to that 15 millikelvin decoherence timeframe we detailed earlier?
That's the billion-dollar question.
If a complex molecular simulation takes an hour to run, but the physical qubit dies in just a few milliseconds, how is any of this computationally possible?
This contradiction is the crux of the entire global endeavor. The realization of decryption-capable machines and utility-scale biological simulators hinges entirely on solving the deepest, most complex core problem in the discipline: quantum error correction.
Because in classical computing, error correction is almost laughably easy. If I want to ensure a 1 stays a 1, I just make 3 backup copies of it in the memory. 1, 1, 1. If a stray cosmic ray strikes the chip and flips one of them to a 0, the computer looks at the register, sees 1, 1, 0, takes a simple majority vote, realizes the 0 is a mistake, and flips it back. It relies entirely on simple redundancy.
But in the realm of quantum mechanics, simple redundancy is physically prohibited. This restriction is dictated by a foundational law known as the no-cloning theorem.
No cloning.
The theorem proves that it is impossible to create an identical independent copy of an unknown arbitrary quantum state. You simply cannot back up a qubit. Furthermore, if you attempt to measure the qubit to see if an error has occurred, you trigger a wave function collapse, instantly destroying the delicate superposition you were trying to preserve.
So you are physically forbidden from backing the data up, and you are physically forbidden from looking at it to see if it's broken, because looking at it breaks it. How on earth do you correct errors in a system you can't observe?
To achieve fault-tolerant quantum computation, or FTQC, engineers implement quantum error correction by entangling a large spatial cluster of unstable physical qubits. This cluster redundantly encodes the information of a single, highly stable virtual entity known as a logical qubit.
Wait, instead of duplicating the data, you smear the essence of the data across a massive web of physical qubits.
Exactly. And to interrogate the system for errors without observing the actual data, you intersperse auxiliary qubits, known as syndrome qubits, throughout the cluster. You repeatedly, continuously measure only these syndrome qubits.
And what do they tell you?
They are mathematically entangled to detect if a bit flip or a phase flip has occurred in their neighboring data qubits without ever revealing the state of the data itself. This allows powerful classical decoders running alongside the quantum chip to identify and correct the errors on the fly without ever directly measuring, and therefore collapsing, the encoded quantum state.
It's akin to carefully running your fingers over the outside of a sealed envelope to determine if the letter inside is crumpled, without ever opening the envelope and reading the sensitive contents.
That's a perfect analogy.
Historically, the industry attempted to achieve this using an architecture called surface codes.
Surface codes are based on a 2D topological lattice. The physical qubits are arranged on a flat, solid-state chip, and they only interact with their immediate adjacent neighbors. From a manufacturing standpoint, they're relatively straightforward to engineer, but their mathematical efficiency is incredibly poor.
Calling it poor is an understatement. To stabilize just one single logical qubit using surface codes, you need upwards of 1,000 physical qubits, a 1,000 to 1 ratio.
It's brutal scaling.
That scaling math is so brutal it made large-scale fault tolerance seem decades, maybe a full century, away. But recently, the paradigm shifted violently.
In 2024 and 2025, the industry witnessed the rapid advent and implementation of QLDPC codes, quantum low-density parity check codes.
This was a massive mathematical breakthrough. What makes QLDPC so fundamentally different?
Well, QLDPC protocols map the error correction pathways across complex, multidimensional mathematical graphs. Implementing these graphs requires non-local connectivity. This means the physical qubits must be able to interact and entangle not just with their immediate neighbors, but across long distances on the processor chip.
Which, physically wiring a chip to allow components to talk across the board without introducing massive noise is an absolute nightmare.
It is vastly more difficult to engineer. However, the mathematical payoff justifies the complexity. QLDPC codes can efficiently encode multiple logical qubits into a single block. It drops that brutal 1,000 to 1 physical to logical overhead ratio by a factor of 10 to 20.
Wow.
Advanced implementations, such as IBM's bivariate bicycle codes and Oratomic's lifted product codes, have taken the concept of FDQC from a distant theoretical dream and brought it drastically closer to near-term reality.
And this rapid advancement in error correction brings us to the grand hardware race. Different corporations are heavily betting on completely different physical modalities to achieve this fault tolerance. Examining the 2025 and 2026 benchmarks is fascinating because every single platform possesses distinct aggressive strengths alongside massive technical weaknesses.
Let's systematically survey the landscape. First, we have superconducting qubits. The major players driving this modality are IBM, Google, and Rigetti.
Their core operational strength is raw speed. We are talking about nanosecond gate execution times. Furthermore, they heavily leverage established semiconductor fabrication techniques. They are printing these intricate chips in clean rooms using methods that feel familiar to classical manufacturing.
But the physical weaknesses are severe. The circuits are extremely noisy. They suffer from high rates of signal crosstalk between the densely packed components on the chip, and as we thoroughly discussed, they strictly mandate the massive infrastructure of a 15 millikelvin cryogenic dilution refrigerator.
Despite the noise, they are leading the pack in several critical metrics. Google's Willow chip successfully crossed the QEC threshold, meaning the algorithmic error correction actually began outpacing the physical errors accumulating in the hardware.
A historic moment.
And IBM has firmly pledged to deliver their Starling system by 2029, explicitly targeting the operation of 200 high-quality logical qubits. So that's superconducting. What about the trapped ion modality pursued by companies like Quantinuum and IonQ?
Trapped ion systems offer exceptionally high natural fidelity. We are seeing sustained 99.99% fidelity on complex 2-qubit gates. Because they use pristine natural atoms suspended in a vacuum, they don't suffer from manufacturing defects like superconducting chips do.
Right.
Crucially, they offer all-to-all connectivity. Any ion trapped in the chain can physically interact with any other ion, which is absolutely perfect for executing those complex QLDPC codes. Additionally, their coherence times are remarkably long.
Because they use perfect atoms, they hold the data beautifully.
Yeah.
But their technical weakness is speed. Because you are physically manipulating an entire heavy atom with dynamic electromagnetic fields and lasers, it's sluggish.
Very sluggish compared to superconducting.
We are talking microsecond gate speeds compared to the blistering nanoseconds of superconducting circuits. Furthermore, scaling up the massive intricate vacuum chambers and the precision laser arrays required to trap thousands of ions simultaneously is an incredibly daunting engineering challenge. Still, they have successfully demonstrated early logical qubits with error rates significantly lower than their underlying physical components. Okay, third major contender. neutral atom architectures, championed by Quera and atom computing.
Neutral atom architectures are highly scalable. They utilize identical atomic qubits, typically rubidium or strontium, and deploy dynamic, highly mobile optical tweezers. These lasers can literally pick up individual atoms and move them around the vacuum chamber mid-computation, offering incredibly dense, reconfigurable arrays.
The density is wild. The Harvard and Quera team recently demonstrated coherent arrays containing over 6,100 atoms. They even showcased a continuous mid-computation atom replenishment system.
Which is brilliant engineering.
If an atom gets accidentally lost from the trap, the system simply slides a fresh atom in to replace it without halting the ongoing calculation. But similar to trapped ions, precisely controlling those intricate, massive laser systems limits the overall gate speeds, and the sheer complexity of the optical setup remains a significant bottleneck. And finally, the fourth major modality, photonic processors, being developed by Cyquantum and Xanadu.
Photonic architecture is completely distinct from the other three. It processes information using the quantum states of light. The massive advantage is that it operates effectively at room temperature. It completely eliminates the need for a dilution refrigerator.
Which is a game changer.
Furthermore, it is naturally networkable because photons already travel seamlessly down standard fiber optic cables. And because photons rarely interact with their environment, they are practically immune to ambient thermal decoherence.
Operating at room temperature and plugging straight into fiber optics sounds like the holy grail. But the fatal flaw of this modality is photon loss. Photons love to simply disappear or scatter into the walls of the waveguides.
They just leak away.
Additionally, creating deterministic multi-qubit entanglement gates using light is exceedingly difficult because photons naturally ignore each other. To mitigate that constant loss, these companies are attempting to aggressively leverage QLDPC codes via novel entanglement-first optical architectures.
Your point about photonic systems being naturally networkable provides an excellent transition to the next hurdle. As the industry scales these massive, distinct computing clusters, perhaps a supercooled, superconducting chip in New York and a room temperature photonic array in London, how do we connect them to share quantum information?
Exactly. If we want to harness distributed computing power, how do these geographically separated machines talk to each other without destroying their fragile quantum states? We are talking about constructing the quantum internet, and this ambition introduces a whole new set of physical impossibilities.
The ultimate goal of the quantum internet is to distribute entanglement across continental and eventually global distances. Achieving this enables blind quantum computing in the cloud, incredibly synchronized global metrology, and absolutely secure quantum key distribution, or QKD.
But there's a problem with standard cables.
However, transmitting delicate quantum data photons carrying complex superpositions through standard silicon glass fiber optic cables is immensely challenging because the light signal naturally attenuates and scatters over long distances.
In our massive classical fiber networks, when a light signal gets weak over a long stretch of ocean, we just install an optical amplifier to copy the signal, boost its strength, and send it further down the line. But we can't do that here.
We cannot, strictly due to the no-cloning theorem we discussed earlier. An optical amplifier fundamentally works by measuring and copying the signal. You cannot copy an unknown quantum state. Therefore, deploying classical optical amplifiers is strictly prohibited by the laws of quantum physics. To construct a long-distance quantum network, engineers must build highly specialized, deeply complex hardware known as the quantum repeater.
If a quantum repeater can't copy the signal to boost it, how does it move the data?
It operates through an intricate, fascinating process called entanglement swapping. A long continental distance is broken down into smaller, physically manageable segments. The repeater establishes an entangled link across just one small segment. It then performs a highly specific joint Bell state measurement between two adjacent segments.
And what does that achieve?
This measurement essentially teleports the quantum state from one node to the next, stepping the entanglement down the line in a synchronized cascade. The crucial aspect is that the quantum information is transmitted across the distance without ever directly measuring the data payload itself, thereby preserving the superposition and strictly obeying the no-cloning theorem.
It's essentially an intricate, perfectly timed bucket brigade of teleportation. And this isn't just theoretical whiteboard physics anymore. There are massive, real-world testbeds achieving wild results right now. Look at the 2025 Chicago Quantum Corridor. Researchers laid down 12 miles of dedicated urban fiber optic cable underneath Chicago. And to synchronize the repeaters and make the network function, they integrated Inflection's ticker optical atomic clocks.
The level of synchronization required to execute entanglement swapping across an urban environment is staggering. The Chicago network successfully achieved picosecond synchronization precision, that is, coordinating actions down to trillionths of a second.
Unbelievable.
Maintaining that level of phase coherence across dynamic fiber networks is absolutely vital, not just for distributed quantum computing, but for proposed future applications like ultra-secure, tamper-proof, high-frequency financial trading.
And across the ocean, the advanced research networks in Delft have established heterogeneous quantum routing. They are utilizing nitrogen vacancy, or NV centers, embedded in synthetic diamonds. They use these tiny, controlled imperfections within the diamond lattice as high-fidelity quantum memory nodes to temporarily hold the fragile state while the entanglement swapping procedure executes. They are actively generating remote entanglement, taking the crucial foundational steps toward bridging disparate quantum computing clusters across the European continent.
These testbeds represent the literal physical foundation of a new global cybernetic infrastructure.
Let's take a moment to reset. We have covered an immense amount of groundbreaking progress, the tantalum coherence breakthroughs, the mathematical elegance of breaking RSA, natively simulating cancer drugs, the foundations of the quantum internet. It sounds unstoppable, but I promised you at the top of the show that we would aggressively separate the extreme hype from physical reality. We need to perform some serious reality checks. Where is quantum actually failing right now? Where has the public hype completely outpaced the underlying science?
The most critical reality check involves dismantling the pervasive myth of broad quantum advantage. The popular narrative constantly suggests that quantum computers will eventually universally replace classical machines. That assumption has been thoroughly and repeatedly disproven.
They won't replace everything.
No. A quantum processor is an incredibly specialized interference engine. It is exceptionally poor at executing general-purpose sequential computing tasks. It will never efficiently run a web server, it will never quickly query a standard SQL database, and it is laughably terrible at basic arithmetic.
A supercooled 15 millikelvin dilution refrigerator is fundamentally worse at adding 2 plus 2 than the free calculator app on your phone. But there's another fascinating, somewhat ironic twist to the hype, a phenomenon known in the field as dequantization.
Dequantization is arguably one of the most counterintuitive phenomena occurring in computer science today. For years, theoretical researchers have enthusiastically published quantum algorithms promising massive exponential speedups for highly complex tasks, particularly in the realms of machine learning or recommendation systems. The industry would celebrate, assuming quantum mechanics had conquered yet another computational domain.
But then, classical computer scientists would closely examine the underlying math of the proposed quantum algorithm and say, wait a minute, this quantum approach just revealed a highly efficient, hidden mathematical structure that we never noticed before. And they used the inspiration from the quantum algorithm to write a highly optimized classical algorithm that runs on regular silicon chips and achieves the exact same massive speedup.
A prime example of this phenomenon is the breakthrough work of researcher Yiwen Tang. She systematically dequantized several of the most highly anticipated quantum machine learning algorithms.
How did she do it?
By creatively utilizing advanced statistical inference techniques and classical tensor networks, she mathematically proved that carefully optimized classical algorithms can entirely keep pace with, and often completely outperform, near-term, error-prone quantum circuits. The theoretical quantum algorithms essentially provided a treasure map that allowed classical computing to win the race.
It completely flips the narrative, turning an expected quantum victory into a classical triumph. And speaking of machine learning, we absolutely have to address the massive global AI boom. Everyone assumes that quantum AI is the inevitable next step for training massive models like LLMs, the large language models that power advanced text and image generation. But there is a massive, fundamental physical bottleneck standing in the way.
Yes. The constraint is known as the input bottleneck. This is a severe physical barrier tied directly to the current lack of fault-tolerant quantum random access memory, or QRAM. To train a massive LLM, you must ingest billions, or increasingly trillions, of parameters of classical text data. Encoding that massive volume of classical data into a delicate quantum state, whether via amplitude encoding or bit encoding, requires an immense amount of time and incredibly deep circuit depth.
The encoding process often scales linearly, O of n, with the sheer size of the data. The computational time it takes to painstakingly load the classical text data into the fragile qubits literally erases any algorithmic speedup the quantum processor would eventually provide once the data is loaded. The machine spends all of its coherence time just reading the dictionary, and the qubits collapse into decoherence long before the machine can write the poem.
Consequently, training massive, data-heavy, deterministic AI models remains vastly more efficient on massive classical GPU clusters. Quantum machine learning will likely remain relegated to highly specialized small dataset problems, such as the high-dimensional gallium nitride semiconductor modeling we discussed earlier.
But to be entirely fair to the physicists dedicating their lives to this, it's not all dequantization and bottlenecks. Pure, verifiable quantum advantage is still a physical reality, particularly when it comes to simulating complex physics.
Absolutely. We must not let the pendulum of reality checks swing too far toward extreme skepticism. In 2025, the Google Quantum AI team utilized their 101 qubit Willow chip to execute the quantum echoes algorithm. They specifically focused on measuring out-of-time order correlators, or OTOCs.
To put that in plain terms, they took a 65-qubit subsystem, injected a state of high chaos, and essentially ran the system forward and backward in time, precisely measuring the complex scrambling of quantum information.
Because classical algorithms require tracking exponentially scaling probability amplitudes to simulate that level of dynamic chaos. Classically simulating that exact 65-qubit calculation would take the world's fastest classical supercomputer, the Frontier system at Oak Ridge National Laboratory, over 3 years to complete.
And how fast did the quantum chip do it?
The Willow chip extracted accurate, verifiable physical data regarding the scrambling dynamics in just 2 hours. That experiment definitively proves that computational utility, well beyond the reach of classical architectures, is a physical reality today.
So the raw computational power is real, but the timeline for scaling that power up to a machine that can break RSA or simulate a new battery chemistry is heavily, heavily disputed. There is an ongoing, honestly quite heated debate in the field regarding when we will actually see a utility-scale, fault-tolerant machine.
The debate highlights the honest, profound uncertainty inherent in frontier physical science. On one side of the argument, you have corporate roadmaps projecting aggressive, relatively linear hardware maturation. IBM, for example, has firmly pledged the delivery of the Starling system, capable of executing 100 million quantum gates across 200 high-quality logical qubits by 2029.
They sound confident.
These massive corporate teams view the remaining engineering hurdles, crosstalk, wiring density, cooling limits, as just that. Hurdles to be iteratively solved with enough capital and engineering hours.
But on the other side of the aisle, you have fiercely independent academic experts and notable theorists. Skeptics like Scott Aronson, John Preskill, and Gil Kalai. They look at the brutal physical reality of controlling tens of thousands of noisy physical qubits, actively suppressing the inevitable hardware crosstalk that emerges as chips get denser, and executing real-time classical decoding within tight microsecond windows. They argue that these are not simple linear engineering problems, they are nonlinear physical walls.
Many of these prominent skeptics believe that utility-scale FTQC may be significantly delayed deep into the 2030s. Some theorists even posit that microscopic noise scaling may present insurmountable fundamental limits, permanently restricting the maximum size of reliable quantum arrays regardless of engineering ingenuity.
And this intense debate bleeds directly into the physical thermodynamics of the hardware, too. We talked at length about the strict requirement for massive 15 millikelvin cryogenic dilution refrigerators. But in late 2025, researchers at Stanford University debuted a highly provocative nanoscale optical device. They utilized a specialized material called molybdenum diselenide patterned directly onto a silicon substrate. And they successfully entangled the spin of photons and electrons at room temperature.
It is a profound, paradigm-challenging proof of concept. Proponents of that specific breakthrough argue it could eventually pave the way for miniaturized, affordable quantum networking components, and perhaps even point toward personal quantum devices that do not require massive vats of liquid helium to operate.
But the condensed matter physics community pushed back hard and immediately. They remain highly skeptical of the scaling potential. They argue that ambient temperature systems will always suffer from chaotic thermal noise, rendering complex multi-qubit gates impossible. They maintain that true, universal, fault-tolerant computing will always strictly require the sterile, perfectly isolated vacuum of a cryogenic environment. They view the Stanford device as brilliant fundamental physics research, but not a viable commercial pathway for scalable computing.
And that precise tension, the friction between aggressive, well-funded corporate engineering roadmaps and the conservative caution dictated by fundamental physics, is exactly what makes this the most dynamic, high-stakes field in modern science today.
We have covered an immense amount of ground today. Let's try to synthesize this massive journey for you. We started by tearing down the persistent sci-fi myth of trying all answers at once, and replaced it with the mathematical reality of the interference engine, the dynamic acoustic resonance of complex probability amplitudes. We explored the brutal thermodynamic realities of operating at 15 millikelvin and the brilliant material science breakthroughs, like swapping aluminum for tantalum on silicon, that are fighting decoherence and keeping the qubits alive.
We deeply examine the very real, very present cybersecurity threat of the HNDL framework harvest, now decrypt later, and the urgent mathematically complex migration to post-quantum cryptography, utilizing high-dimensional lattice structures to protect the global internet from Shor's algorithm.
We looked at the revolutionary mathematical leaps in QLDPC error correction, dropping the physical overhead of fault tolerance, and the world-changing potential of natively simulating molecular biology for advanced drug discovery and next-generation battery chemistries. We're truly watching the second quantum revolution transition from a theoretical physics chalkboard into the crucible of advanced multidisciplinary global engineering.
If I may, I want to leave you with a final, perhaps slightly philosophical thought to ponder. We discussed Richard Feynman's postulate earlier, that nature is fundamentally quantum, and therefore strictly requires a quantum machine to simulate it flawlessly.
Right, the universe isn't built on classical silicon bits.
If the ultimate eventual purpose of this specific technology is to achieve a perfect one-to-one simulation of nature at the absolute subatomic level, and our universe itself operates fundamentally on these exact same probabilistic quantum rules, what does it truly mean when humanity successfully builds a machine that can perfectly emulate the underlying code of reality itself? When we mathematically map a highly complex molecule perfectly onto a fault-tolerant qubit array, are we simply building a vastly superior calculator? Or, by mastering and manipulating the deepest physical laws of information processing, are we essentially building a miniature, fully realized universe inside a cryogenic box?
That is exactly the kind of question that makes diving deep into this field so intoxicating. It completely blurs the line between advanced computing, fundamental physics, and philosophy. Thank you for joining us on this exhaustive episode of Audio Notebook. Remember to stay curious, keep questioning the impossible, and keep exploring the very edges of what we know.